Okay, so it's my pleasure to welcome Professor Francesco Bonsante, who is a professor at the University of Pavia, Italy. He got his PhD in 2005 from Scuola Normale Superiore di Pisa, and then he spent some time there on research position. Then in 2007, he got the position at Pavia, and since then he's also very active on the international level. He gave numerous talks at conferences, workshops, and during his research visits in various universities. And in fact, we met that way. That is, a student from our university was at the summer school in Italy, and he was so impressed by a lecture by Professor Bonsante, and he told me, you must invite him to our school. So I did it. Professor Bonsante is interested in hyperbolic geometry, Lorentzian geometry, low-dimensional geometry, that is 2- and 3-dimensional. And among his main results, there is a complete characterization of surfaces of constant mean curvature properly embedded in Minkowski spaces of any dimension. Francesco, the floor is yours, please.
Okay, thank you very much. Thank you very much for the presentation, and thank you for giving me the opportunity to talk in this conference. I'm really sorry to not be there. I was not able to come, and nonetheless, I hope you can enjoy my presentation. Okay, when I chosen the topic, so I want to talk about rigidity because I think that rigidity is kind of main theme in geometry. It is a kind of recurrent theme. Many problems in geometry are rigidity problems. And in particular, rigidity of convex surfaces is kind of a very popular and very classical theme. But when I decided to talk about this topic, I had in mind to talk about more recent result. But then I realized that maybe the idea I wanted to communicate to you are already contained in some very classical theorems about surfaces in the Euclidean spaces. And those surfaces in the Euclidean spaces are probably more, are simpler objects. So I decided to spend big part of this talk about talking about convex surfaces in the Euclidean spaces. And just if I have time, in the last part of the talk, I will say something about the rigidity of convex surfaces in hyperbolic space. So, okay, I will start from a very first of all, I want to say something about a very simple case, a baby case, let's say, that is a 2-dimensional case. It's the flexibility of polygons. So I think it's a common experience that there are polygons which are not congruent, but which has the same length of, such that their edges have the same length. In other words, I think you can say in this way that if you build a polygon with some rigid bars, usually you can deform it. The angles are not constrained by are not determined by the length of the edges. Okay, this is the flexibility I have in mind. And I want to introduce, I want to express this notion in a more mathematical language. And in particular, I want to express this fact in such a way, in a way that is not really trying to not use so much the fact that we are dealing with polygons. So I give you this definition. We take two polygons on the plane. So this is the first attempt. This is not the definition I want to give in the end, but let's give this very simple definition. You take two polygons on the plane. You say that an isometry between the boundaries is just a homeomorphism between the boundaries, which preserve the length of any connected arc contained in the boundary of the polygon. Okay. And okay, this definition really do not translate the fact that the two polygons are made by the same rigid bars, because here there is a very nice simple picture that you can make. You can take this triangle and then you can pull points 2, 4, and 6 away from the triangle and construct an hexagon. And you can do this without changing the length of any arc contained in the boundary of the polygon. So the boundary of this triangle and the boundary of the hexagon are isometric. Okay, so indeed, it's a simple exercise to check that two polygons have isometric boundaries if and only if the perimeter of the boundaries are equal. So that's this notion of isometry in this setting is really weak. Okay, but it has the advantage that you don't use the fact that this notion really do not rely on the fact that we are talking of polygons. It's very general. So now you can refine a little bit the definition. You say that an isometry is simplicial when it sends vertices to vertices and edges to edges. So for instance, this is not a simplicial isometry because the points, the edge 1, 5 is not sent to an edge, it's sent to a couple of edges. Okay. So indeed, it's easy to see that the boundaries of two polygons are simplically isometric, basically when they have when their edges have the same length, so when they are made by the same rigid bars attached in the same order, but possibly forming different angles. Okay. Okay, and you say that a polygon is simplically rigid if anytime you have another polygon whose boundary is simplically isometric to the boundary of P, then P prime is really congruent to P. It has the same shape. So the structure on the boundary determines the shape of the polygon. Okay, is this clear? Okay. And of course, you say that the polygon is rigid if every time you have another polygon which was boundary is isometric to P, then P prime is congruent to P. And okay, now it's probably it's well known that the only simplically rigid polygons are the triangles. So the triangles are the only polygons that when you build a triangle with some rigid bars, you cannot deform it. So the angles are determined by the length of the edges. But this is not true for quadrilaterals or pentagons or other polygons. And indeed, no polygon is rigid. And the fact that it is not rigid is just because isometry in this context is too weak. Given any polygon, you can construct a different polygon with the same perimeter. And so this new polygon will be, the boundaries of the two polygons will be isometric, but of course, in this context, rigidity, this simple rigidity. Okay, are there questions so far? Is it clear? Okay, now we upgrade to dimension 3, and dimension 3, first of all, we will consider polyhedron, convex polyhedron. What is a convex polyhedron? Is basically the convex hull of a finite collection of points that are in generic position so that this convex hull has not empty interior. And okay. Is there a question?
Yes, there is a question.
Yes, could we go back to the previous slide?
Yes.
Could you give some example of two-dimensional shape which is rigid, not simply rigid, but rigid?
I don't hear you very well. Can you speak louder, please?
Yes. Could you give an example of something two-dimensional which is rigid in this sense?
No, there is no rigidity in dimension 2. There is no rigidity.
No rigidity at all. Not only for polygons, not at all.
Not at all. I think there is no rigidity because in dimension, basically in dimension 2, the only invariant is so I mean, among reasonable objects, even if you take, I think, convex object, I think that the only invariant is the length of the boundary. If two convex curve has the same length, then they are isometric according to my definition. So it's a very weak condition in dimension 2. We will see that in dimension 3 things are much richer, but in dimension 2 this rigidity is mostly it's not very interesting. I mention it just because in dimension 3 we will see it will be we will have some amazing results, I think.
Okay, thank you.
So a polyhedron, it's just this. Okay, I think you know what is a polyhedron. And the border of a polyhedron is a union of polygons that are called faces, convex polygons. Okay. And basically, along each edge of a polyhedron, each edge of the polyhedron is in the boundary of exactly two faces. And these two faces, you can measure how are bent by the dihedral angle. The dihedral angle is the angle that you get intersecting the polyhedron with some plane, which is orthogonal to the edge. So it's a number attached to each edge of the polyhedron, which measure how much the two faces are bent. So somehow it's the analog of the angles for polygons. Okay? Now, again, you can say, even in this context, you can introduce a notion of isometry between the boundaries of two polyhedra. Exactly as before is a homeomorphism which preserves the length of paths contained in the polygons. Okay. And you say that an isometry is simplicial if it also preserves the structure of the boundary of polyhedra. So it sends faces to faces, edges to edges, and vertices to vertices. Okay, maybe I should remark, this is maybe intuitive, but not immediate, if you want to give a proof, that if you have an isometry between the boundaries of two polyhedra, it will send vertices to vertices. Any isometry between the boundaries of two polyhedra necessarily sends vertices to vertices. I will explain this a little bit later, but this already should show that there is a big difference with respect to the previous case. Okay, vertices are real special point from this point of view. Okay, from this metric point of view. Are there questions? Okay. Again, this simplicial isometry can translate some, can be also rephrased in a more common language. So assume that the boundary of polyhedra is made by some rigid material, then two polyhedral are simplically isometric if you can basically using the same, the same faces, you can transform the first polyhedra into the other polyhedras, just changing the dihedral angles. Okay, and you can ask whether here you have rigidity or not, and well, there is this very old theorem due to Cauchy, which says that here you have a lot of rigidity. So if you have two convex polyhedra, whose boundaries are simplically isometric, then they are congruent. So polyhedral are rigid objects. And this makes a big difference with respect to polygons. At least so far, simplicity rigid, according to our definition. Okay? Later in this talk, I want to spend some time explaining something about the proof of this theorem, because I think that the proof of this theorem is really beautiful and even simple. And but before, let me stress that here convexity is really a crucial point, because otherwise you can construct easily a counterexample. So you take this polyhedron. This polyhedron is just obtained by as the union of a cube and a pyramid. Okay, and now the second domain is obtained by basically removing the same pyramid from the cube, okay, with the vertex on the bottom this time. Okay, the second one is not convex. The first one is convex. And of course, these two objects are not congruent, but of course, the boundaries of these two objects are made by the same faces. So this is not a counterexample to Cauchy theorem, because Cauchy theorem requires that both Q and Q prime are convex. Okay? Are there questions? Okay. Now, indeed, this theorem has had a lot of generalization in a wider context of surfaces in the Euclidean space. Again, if you have, okay, two surfaces in the Euclidean space, an isometry, again, can be defined as just a homeomorphism which preserves the length of paths. Of course, okay, this definition does not require that the surfaces are smooth. Of course, the definition is interesting when you can imagine some wild cases where basically you do not have paths of finite length joining points. And so in that case, the definition is not so interesting. But if you have some kind of very mild regularity, if you remove the wild examples, this definition makes sense and it's interesting, even if the surfaces are not smooth. Okay. And okay, of course, a surface is convex. I will say that a surface is convex when it bounds a compact convex domain in the Euclidean space. This will be my definition of convex surface today. And in particular, convex surfaces are topologically just a sphere. Moreover, in general, they are not smooth, but they are locally graph or Lipschitz function. So they are Lipschitz surfaces. And so the definition of isometry in this context is really meaningful. You have a lot of paths connecting points on a convex surface with finite length. So, okay. In particular, when the surfaces are sufficiently smooth, are at least C1, then basically an isometry is just a C1 map which preserves the first fundamental. So you recover maybe a more analytic definition of an isometry. And yeah, preserving the first fundamental form, what I mean is that if you take any local parameterization sigma of S, then composing sigma by F, you get some local C1 parameterization of S prime, and the first fundamental form expressed in these parameterizations agree. Okay. Other questions?
There is some domain in the plane, yes?
Can you speak louder?
Yes,
I don't...
omega is some domain in the plane, yes? Two-dimensional domain.
No, I don't hear you.
Once again, omega is...
Yes? Omega is an open subset of the plane, yes.
Okay, thank you.
Yeah, sorry. Omega here is some open subset. This is really a local parameterization, so omega is an open subset of the planes. Thank you. Okay, and now we have these two theorems, actually. So the first one tells you that if you have two surfaces that are at least C2, sorry, two convex surfaces that are at least C2, and which are isometric, so there is a map between them which preserve the length of paths, then they are congruent. Okay. And this theorem was first proved by Cohen and Vossen in 1936 and in the analytic setting, and then by Erglotz in 1943 in the C2 case. And 20 years later, Pogorelov proved this amazing theorem, removing any regularity assumption. If you have two surfaces, convex surfaces, which are isometric, according to our definition, then they are congruent. This is really amazing theorem. In particular, this theorem applied to polyhedra. And it tells you that convex polyhedral are not only simplically rigid, this was already known by Cauchy, but they are rigid. If you have an abstract isometry between the boundaries of two polyhedra, which does not preserve, in principle, faces or edges, this isometry is, indeed, the two polyhedra have the same shape. You see the main difference, the big difference with respect to the two-dimensional case. Okay, let me also notice that in this theorem, the compactness of our surfaces is really necessary, is kind of key assumption. Otherwise, it's easy to find counterexample, like you can take two convex curve on the plane having the same length. So they are isometric, gamma and gamma prime. Gamma prime, sorry, I forgot to put here gamma prime on the second curve. And then you can make two cylinders based on this curve in the Euclidean space. And it's easy to see that those are, I mean, isometric, that there is a map preserving between the boundaries of these two cylinders, which preserve the length of each path, okay? But of course, they have a different shape. So for Pogorelov and for these theorems, you really need that you are dealing with closest surfaces. And this also, I mean, suggests that the kind of result behind this theorem is not of local nature. You cannot expect that you have some local rigidity. And it's you need to use at some point some global assumption about the fact that you are dealing with compact surfaces. Okay, are there questions so far? Okay.
Well, in fact, yes. Please go to the previous slide.
Previous?
One again. What do you mean by surface if you do not assume C1, or what do you mean by a surface?
What I said at the very beginning, it's anytime you have a map between the homeomorphism without the boundary of two convex surfaces, without two convex surfaces, which preserve the length of the path contained in each surface. And the length makes sense for any continuous curve. Sometimes it can be in plus infinity, but it makes sense for any continuous curve.
The surface is just an image of a homomorphism or of a continuous map, which is...
So if alpha is a continuous path in S, f of alpha, f composite by alpha, maybe I should be, if you want to be more precise.
Okay, I understand length, but what do you mean by a surface in 3?
What I mean by isometry?
not isometry, surface. If you don't know, if we assume C1, then I know what is the surface, okay? So you assume that that maps are just continuous, the manifold with just continuous maps, or
so here, so you are talking about this Pogorelov statement.
yes. So what do we assume? Okay, intuitively, okay, everybody understands.
No, I am assuming that so S and S prime are two surfaces in the Euclidean space which bound some convex domain. And you assume there is some abstract homeomorphism between the two boundaries which preserve the length of the path. And you can conclude then there is a global isometry of the Euclidean space moving the surface S on the surface S prime. Is it not clear?
No, all this is clear. I mean, for the others are clear for me, but I just wonder, intuitively, I understand what is a surface in R3, okay? But what would be the precise definition of a surface in R3? That's the surface, not the isometry, not the length, that's the surface.
Unfortunately, I don't hear you well. I don't know why, but I have some problem hearing you. So you don't understand. Can you say it again?
Okay, let's go further. Maybe we can come to that question. Please continue.
Okay. Sorry. Okay, now I want to spend some time explaining the strategy of this Cauchy theorem. Again, Cauchy theorem says something simpler. Say that if you have two convex polyhedral, whose boundary are simplically isometric, so basically the boundary are made by the same polygons, arranged on the same way, but the only thing that change are the dihedral angles in principle, then they are congruent. Then you want to prove that indeed they are congruent. Okay. And so you assume that you have the simplicial isometry between the boundaries of these two polyhedra, and you label each edge of Q with plus, minus, or 0 according to the change of the dihedral angle when you go from Q to Q prime. In particular, if the dihedral angle increase, then you put plus. If the dihedral angle decrease, you put minus, and otherwise you put 0. So this gives you a decoration on the of this graph of made by the edges of the polyhedron Q. Okay? And of course, we want to prove that this decoration is just made by 0, because in this way I will prove that I'm not changing the dihedral angles going from Q to Q prime. And from this, it's very simple to convince yourself that Q and Q prime has the same shape, because you can fix one face on Q and move this face to the corresponding face of Q prime. And since the dihedral angles are equal, of corresponding edges are equal, this rigid motion automatically will send adjacent face to the face that you have fixed to faces of the polygon Q prime. And then you continue in this way, you see that the whole polyhedron Q is sent to the polyhedron Q prime by this rigid motion, okay? And okay, so really the goal of Cauchy theorem is to prove that all edges are labeled by 0. Now you consider now the graph gamma f obtained as the union of edges labeled by plus or minus. So you just consider the edges where you change the dihedral angles. Now, if O is a vertex of gamma, so the first lemma tells you that So this is the geometric lemma. Here you have to use the geometry of this polyhedra. It tells you that if O is a vertex of this graph, then when you go around O, you will see some vertices of gamma f, and some vertices will be labeled by plus, some vertices, so some edges will be labeled by plus, some edges will be labeled by minus, and you just count the number of times you see a change of sign. So here you see a change of sign because you have plus or minus. Here you see a change of sign because you have plus or minus. Here you see a change of sign because you have plus or minus, and so on. Okay, and the geometric lemma tells you that on gamma f, for every vertex, so you see at least any 4 change of sign. Okay. So if you count the total number of this geometric lemma, tells you that if you count the total number of change of sign that you can count looking at every vertex of gamma f, this will be at least 4 times the number of vertices. Okay. Okay, I should say that this lemma really rely on the fact that gamma f is constructed in this way. Here we will use the geometry to prove this lemma, but it's something as a local nature, this lemma, because you just have to count what happens around a single vertex. You can localize the problem around a single vertex.
A question in the chat.
You have a question?
There is a question in the chat.
There is a question in the chat. Okay, sorry. Let me open the chat. A precise definition of a surface. That's a good sorry, good point. I didn't get it. I mean, if you want a topological surface embedded in the Euclidean space, but for us, our surfaces will be Lipschitz continuous, so they really are locally graph of Lipschitz function. So at the very end of the day, for me, it's just the boundary of a convex subset. So, okay.
Okay, thank you very much.
Okay, so this is the first ingredient. And the second ingredient is just a topological lemma, it's just combinatorial lemma somehow. It tells you that if you take any non-empty graph on the sphere without bigons, I don't want to say what it is. This is a technical condition, but for us it's free. For our graph, it's free. And you label as you want the edges of gamma by plus or minus, then the total number of change of sign that you can get is 4 times the number of vertices minus 8. So it's strictly smaller than 4 times the number of vertices. And so this is, as I said, is a combinatorial lemma which has a global nature. It's not something that you can prove locally. And using together the geometric and the topological lemma, you conclude that if you have a simplicial isometry, then gamma f must be empty. Otherwise, you get a contradiction because the geometric lemma tells you that the total number of change of sign is at least 4 times the number of vertices, and the topological lemma tells you that it must be strictly less. Okay? And so from this, you get that the dihedral angles are preserved, and you conclude the proof of the Cauchy theorem. Okay. Now, I will spend a few words about this geometric lemma, which seems mysterious, but it's not so mysterious when you think a little bit. So I need to introduce this definition of a spherical polygon. A simplicial cone is basically just a cone with vertex at 0 bounded by the finite collection of planes. So here, this is a simplicial cone bounded by 3 planes. And a spherical polygon is basically the intersection of a simplicial cone with a sphere of, let's say, of radius 1, just to normalize things, with vertex at the vertex of the polygon, with center, sorry, of the sphere at the vertex of the polygon. So if we have this simplicial cone, this gives me this spherical polygon, which is a spherical triangle. And I will notice that the length of the edges of this polygon really corresponds to the angles of the faces of the cone, while the angle of the spherical cone corresponds to the dihedral angle of this cone. Is it clear? Okay. Of course, anytime you have a polyhedron around each, around each vertex, you see a simplicial cone. So you can intersect the simplicial cone by a sphere and get a polygon. This is what I will call the link of Q at O, and this will be a spherical polygon. So for instance, if you take the regular tetrahedron, the link around a vertex will be a spherical triangle whose length will be pi over 3, because the angle of each triangle of the tetrahedron is, of course, pi over 3, and the angle of the spherical triangle of this link will be equal to the dihedral angle of the tetrahedron, which you can compute is some number. Okay. Now, if you have a simplicial isometry between the boundaries of two, we come back to our problem, we have a simplicial isometry between the boundaries of two polyhedra, and you want to compare the spherical polygons that you associate to a vertex and the corresponding vertex. Of course, since the length of the spherical polygons corresponds to the angles that you see in each face, and since the simplicial isometry preserves sends in a rigid way each face to a face, to the corresponding face, you see easily that the length of the edges of the spherical polygons are preserved by the simplicial isometry. But the angles are not, because the angles of the spherical polygons really depends corresponds to the dihedral angles, and in principle we know that the dihedral angles change. Okay. Anyway, if you on some edge you see the sign plus, then you can say that the angle of the spherical polygon corresponding to Q prime is bigger than the corresponding angle in Q, because you are increasing the dihedral angle, and the dihedral angle is also the angle that you see on the spherical polygon. Okay, is it clear? Okay, and now, so you can, our geometric lemma is really a consequence of this two-dimensional proposition that tells you that if you take two convex spherical polygons with the same number of vertices and such that the corresponding edges are equal, so exactly the situation that we have that comes from our setting, and you label each vertex of P by plus or minus according to the change of the angle, exactly as we have done before, then around the boundary of P, you see at least 4 changes of sign. So this is the kind of result that you have to prove the geometry. This is kind of, I'm basically restating the geometric lemma just in purely two-dimensional geometry. Okay, is it clear? And now, why this is true? The proof of this is based on what people call arm lemma. Okay, here there is a formal statement, but this lemma tells you something which is very intuitive. Assume that you have a mechanic arm made by n rigid bars that are hinged together, And it's, I think, intuitive that the more, as long as my mechanic arm describes some convex curve, the more I open the arm, which means the more I open the angles between the hinges, the more the distance between the endpoints increase. Okay, and if you want to say this formally, if you have two, let's say spherical, but this is true also in the Euclidean setting, the two spherical polygons with the same number of vertices, such that A1, A2 is equal to A1 prime, A2 prime, etc., until AN minus 1 AN is equal to AN minus 1 prime and AN prime, but such that the angle on the left are smaller than the angle on the right, then the distance between A1 and AN is smaller than the distance between A1 prime and AN prime, except, and you have equality if and only if the angles are all the same. Okay? This is what is called arm length. I hope that you understand the simple geometric meaning without the statement, behind this statement. Then, okay. And okay, the proof of this lemma is the statement, I think, is very simple, but the proof is a bit technical. We'll completely skip it. But now from arm lemma is easy to prove the proposition, because now you assume the proposition tells you, so you assume that you have two convex spherical polygons with the same, such that the edge length are the same. The edges have the same length. And you look at the region where, you put plus or minus or 0 on each edge according to the change of the angle when you go from P to P prime. And of course, there will be some region when you just see plus or 0, some region where you see minus or 0. And they will be alternating. So a region where you see just plus or 0 will be bounded by a region where you just see minus or 0 and so on. And so at the very end of the day, if you don't see four changes of sign, then you have just two regions, or maybe just one, but one is a subcase of two. And a region where you just have plus or 0, and a region where you have minus or 0. Okay. And so there are two vertices, P1 and Pk, let's say, which disconnect these two regions. You take the edge, the segment between P1 and Pk's, and this segment will disconnect my polygon in two polygons, P plus and P minus. Okay. Okay. And on P plus, all angles will increase when you go to the corresponding P plus prime, and on P minus, all the angles will decrease when you go to P. But the edges, the length of the edges of the black edges will be preserved going to P prime. Okay, and so from the arm length lemma, you get that the distance between P1 and Pk is smaller than the distance between the corresponding point on the second polygon. But when you apply the same arm length to P minus, on P minus, I'm closing the arm. So you will get that the distance between P1 and Pk is bigger than the distance between P1 prime, Pk prime. And so in the end, you get that P1, the distance between, comparing these two facts, you conclude that the distance between P1 and Pk is equal to the distance of P1 prime, Pk prime, and again you apply the arm length lemma, and you conclude that all the angles are the same. Okay, and this concludes the proof of the geometric lemma. I hope that this is clear. You have questions? Okay. Now, what about the topological lemma? The topological lemma is a consequence of the Euler formula, basically. I will give a sketch of the proof also of this topological lemma, just to, I want to convince you, really, I want to give the proof just to convince you that you have to use some global, and Euler formula is really a global info, gives you some global information about the surface. So again, the statement is you take any non-empty graph without bigons, whatever it means, and you label the edges of this graph with plus or minus, and you want to check that the total number of change of signs is smaller than 4 times the number of vertices minus 8. Okay, and I will give a sketch of the proof, assuming that gamma here is really the union of all edges of polyhedron. This is, of course, the proof becomes more technical if you want to prove for a more general graph. But I think that for our aim, this is sufficient. And you take V is, so this is the proof given with this assumption that if you want, gamma is a graph which disconnects the surface in simply connected regions. You consider by V the number of vertices, by E the number of edges, and by F the number of faces of gamma, and by Fk the number of faces with exactly k edges. Okay, these faces are kinds of polygons, for us are polygons, and so Fk is just the number of polygons or faces which are polygons with k edges. With k, of course, is any number must be at least 3. And n is the total number of change of sign. Okay, now, of course, in each polygon, how many change of sign you can see? Well, they cannot be bigger than the number of, I mean, on each vertex, I can see 1 change of sign. So it cannot be bigger than the change, than the number of vertices, the number of edges or number of vertices. And if k is even, this number can be reached because you can imagine that plus or minus are alternating on edges. So in this case, you get just k. But if k is odd, this is not possible. So in that case, the bound, the number of change of sign that you see in a face with k edges is at most k minus 1. So for instance, on the triangle, I can have at most 2 change of sign. So the total number n is estimated from above by 2 times the number of triangle plus 4 the number of quadrilateral faces plus 4 the number of pentagonal faces, etc. Okay? On the other hand, if you count for each face the total number of edges and you sum all these numbers, you get this number here, the sum of kf, the sum of kfk, you are counting each edge of the polyhedral 2 times because each edge occurs in the boundary of 2 faces. And also the number of faces is equal to the sum of the number of faces with k edges. And now you put this to formula inside the Euler formula. I recall you that the Euler formula tells you that V minus C plus F is equal to 2 for a polyhedron. And so you put this information, you get that 4 times the number of vertices is equal to the sum over 2k minus 4 fk plus 8. And now this sum is equal to, you can expand this sum, and you get that this is equal to 2f3 plus 4f4 plus 6 f5 plus 8 f6, etc. And this number so is bigger than n because n was 2f3 plus 4f4 plus 4f5, etc. And so put it together everything, you get that 4v is bigger than n plus 8. That is what you need. Okay? Other questions about the proof of this? So the computation is maybe not so interesting. What I really want to emphasize that here, to prove this topological lemma, you need some global fact about your surface. It's not a local you cannot hope to have a local proof of this fact. Okay. Now, we can go a bit further. So now I proved the rigidity statement I want to talk. And I want to explain this while problem that is old but very interesting problem. While realized, okay, this is easy, remark that if you have a convex surface in the Euclidean space, okay, its curvature, which is an intrinsic invariant, as you know, is non-negative. Here now I'm talking about smooth convex surface. This curvature is not negative. So, and he asked this question. I take any Riemannian matrix. A Riemannian matrix is kind of abstract first fundamental form on the sphere with positive curvature. He asked, is there a convex surface in the Euclidean space which is isometric to S2 equipped with this metric? Okay, if what we know what Cohen rigidity proved is that if it exists, it is basically unique up to rigid motion of Euclidean space. But does it exist? Okay, that's a beautiful question. So I take an abstract metric. You can ask why here I put non-negative, here why I'm putting positive. This is really, I think there is a subtle point here that it's important to remark. The point is that behind, so if you want to solve this problem, you can rephrase it in terms of solution of some PDE. And the point is that if the curvature is only non-negative, so when it is 0, this PDE becomes degenerate. And the problem becomes much harder. So positive here is required to keep the problem from the analytic point of view an elliptic problem. And actually, the question has a positive answer. And so somehow, so the question, this is due to a number of people. So again, Lewy proved the result for analytic metric, and then Nirenberg gave a proof for C2 metric. Again, then Alexandrov and Pogorelov gave a different proof using different arguments. And this in particular tells you that studying sufficiently smooth convex surfaces in the Euclidean space is equivalent to study sufficiently smooth Riemannian metric on the sphere is almost equivalent with positive curvature. As long you have this little gap that here you can get something non-negative, here you are stick with positive curvature. Okay. And actually, Alexandrov proposed a version of this Weil problem for polyhedra, because given a polyhedron, the metric structure around every point except vertex is really Euclidean. Okay, what I mean is that any point on the boundary of a polyhedron admits an open neighbor which is isometric according to the definition that I gave before, to an open subset of the Euclidean plane. Okay, this is obvious for points inside the face because they are already contained in some planar region. And for points which are contained in an edge, you can, of course, unbend the edge. You can locally, you just see two faces, you can unbend the faces. And this procedure, of course, preserves the length of any path contained. So this gives an isometry. But if you cannot do something like that around vertices, because if you try to embed around the vertex, so every face will be sent to a sector. So for instance, you take now a vertex of a cube, every face of the cube will be sent to a sector forming an angle equal to pi over 2. And of course, when you try to close the isometry, this three sector does not fill a neighborhood of 0 on the plane. So really, this vertex is not isometric to an open subset of the plane, but is isometric to it has a neighborhood which is isometric to a cone, where a cone here, I mean really a cone in the Euclidean space, a certain cone. Okay, a certain convex cone. Is it clear? Okay, and so Alexandrov proposed this definition: a flat structure on the sphere is given by a finite collection of points, and a flat metric, a metric which is locally isometric to the Euclidean metric, on the complement of this point, such that the metric structure that you see around the point is the one of a convex cone in the Euclidean space. And this is what we will call a flat cone structure on the sphere. And again, Alexandrov proved that if you fix any flat cone structure on the sphere, there exists a unique polyhedron Q on the Euclidean space, which is isometric to this flat cone structure. So again, studying polyhedra up to congruence is equivalent to study flat cone structure on the sphere up to isometry. Okay? Other question? Okay. Now, in the few, I still have, I think, 6 minutes. In these 6 minutes, I will send you, I will say something about convex subsets, convex surfaces in more general space form. In particular, a space form is a Riemannian or pseudo-Riemannian manifold with constant sectional curvature. And today I will just consider the hyperbolic plane, that is the Riemannian space form of constant sectional curvature -1. These space forms are the Riemannian or pseudo-Riemannian manifold with the biggest isometry group possible. So I mean that you have global isotropy. You can, by isometry, you can move any point to any other point, and any tangent vector of unitary tangent vector to any any other unitary tangent vector. Okay. So the hyperbolic space is very important from many points of view. And okay, this is the formal definition. On the topological point of view, is just a round ball with a metric which diverge on the boundary. Okay, and convex sets make sense. So this hyperbolic space share a lot of analogies with the Euclidean space, in particular, given 2 points. There is a unique geodesic segment joining these 2 points. So convex sets make sense also in this setting. And the boundary of convex sets are still, I mean, objects, surfaces, topological surfaces, which are locally graph of Lipschitz functions, somehow, Lipschitz continuous surfaces. And indeed, if these surfaces are smooth enough to talk of curvature, the intrinsic curvature of the boundary of a convex subset is bigger than the ambient curvature, like in the Euclidean case. In the Euclidean case, you have 0 because the ambient curvature is 0. Here, the ambient curvature is -1, and you get the same kind of bound. And again, also the notion of convex polyhedron makes sense in this setting. And the boundary of a convex polyhedron actually inherits a hyperbolic construction. So it has around each point that is not a vertex is locally isometric to a hyperbolic plane. And around each vertex, you have the structure of a cone in hyperbolic space that I'm not defining, but it's a kind of analog of the Euclidean case. And so you can ask Weil problem and also Alexandrov theorem in this setting, and they both also. And indeed also Cauchy theorem, you have rigidity exactly as in the Euclidean setting. And however here, the point is that since the curvature is of the boundary of a convex set is bigger than some negative constant, you can construct more examples somehow. In particular, I want to mention this nice result by Schlenker. Okay, maybe then I will stop because my timing is finishing. Now you take, this is with a more global, I mean, flavor. You take two Riemannian metrics on a, two Riemannian metrics now on the surface with genus T, so a surface with the holes, and such that the curvature is bigger than -1, okay? And then Schlenker tells you that there is an hyperbolic metric on this three-dimensional manifold, sigma cross -1, 1, such that the boundaries, so this metric is convex in the sense that the boundaries of these are locally convex surfaces. And the metric induced by H on each boundary component is the one that you have fixed, is the one isometric to the one that you have fixed. And moreover, H is unique up to isometry. Again, this is a theorem which has the same flavor as the Weil problem. The metric on the boundary, when you have a convex object, the metric of the boundary determines the structure inside, and indeed you are basically free to choose this metric on the boundary. And okay, I think that my time is finished, so I will stop here. Okay, thank you very much.
Thank you very much. Francesco, before we start questions, I would like to ask you, because we have a suspicion that maybe we are not heard very well on Zoom. So when I was giving introduction of yours, could you hear me well?
Yes, now I can hear you better. Yes, thank you.
Now it's better?
Yes.
Ah, okay. Okay. Well, so now let's ask questions. So are there any questions or comments, please? No questions? Okay, some questions from people on Zoom. Okay. Well, so thank you very much again for the talk.
Thank you.